We physicists have held up 100 years, beginning around 1916, for this photograph. It is a nearby black hole, which might just be one of the most charming and puzzling characteristics in the universe. They are tremendous beasts concerning gravity but, simultaneously, for all intents and purposes, intangible to us. A black hole, weighing perhaps 2 to 4 million times the mass of the Sun. Anyway, considering the investigation that was placed into them over the last 20 or 30 years, we've gone from knowing, in a real sense, nothing about them to progressively figuring out more. Exceptionally close, things have recently gotten even crazier. Michio Kaku recently detailed that we, at last, got a look at what's inside a black hole, and this new information sheds light on the nuances the world of science could have missed from the beginning. Go along with us as we dig further into black holes and reveal what's inside. Space, it is tremendous and dreadful. What are black holes? Before we get into the nuances of what Michio Kaku found, we have to talk about the basics. Although the vast majority of us have some idea of what black holes are, there are still a couple of gaps in the right information. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. Around that time, the idea of black holes was totally theoretical. It required an extra 50 years for established researchers to find evidence that black holes, in fact, exist. This happened during the 1960s when scientists were studying the star X1, a magnificent body, and saw an oddly bright blue star that was emitting X-rays. This star was certainly not a lifeless object but was orbiting a giant black something. Upon further assessment, it was seen that the X-rays weren't simply moving around on their own, they were being sucked into the black thing they were orbiting. Thus, the name black hole. This discovery was enormous since it provided proof that black holes truly exist and weren't just an invention of Albert Einstein's wild imagination. While that was incredible, it also meant that there was this fascinating substance in space that we urgently needed to learn more about. So, scientists from one side of the planet to the next got to work. This black hole was named Cygnus X1, and it is situated in the constellation of Cygnus, about 6,000 light-years from Earth. It was no small discovery, it's many times brighter than the Sun and, of course, incredibly dense, which gives it a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. For this reason, it is known as a black hole. The concept of a black hole is both charming and startling. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, gone forever. However, that element of danger makes it even more important to learn everything there is to know about them. Was this it, or were we just beginning? The answer turned out to be the latter. After the discovery of Cygnus X1, scientists began to search for other black holes. They found that there may be almost 100 million black holes in the Milky Way alone. However, since they are so incredibly difficult to identify, we still don't have an exact number. Apparently, there are a few million black holes in the Milky Way, in our own galaxy, which makes them even more important to study. The power of gravity. The main thing with black holes is always going to be gravity. Their gravitational pull is so extraordinary that anything that enters gets crushed down immensely until it becomes a singularity. In simpler terms, black holes are like massive vacuum cleaners that suck everything in. One of the scariest parts about studying black holes is the fact that if someone were to fall into one, they would reach a point where they become a singular line. This process would occur slowly, and the individual would die before the true breakdown of reality occurs. So, let's just say that no one should step into one. But they're all over. Could we be in danger? Despite the fact that the closest black hole to Earth is nearly 500 light-years away, it's still close enough to raise many concerns. In 2021, researchers were able to produce the first clear photograph of a black hole, the M87 black hole. This black hole was captured over several nights, and with every photograph, the researchers gathered more and more evidence about it. They had to line up the individual photographs to fill in all the gaps. In doing so, they were able to confirm that there are 3 layers to a black hole. It's not just one single expanding hole of nothingness, as many people believe, things are much more complicated than that. To even get to the nothingness part of a black hole, you have to survive the first 2 layers. 1. The event horizon. This is the final boundary. Once you pass the event horizon, moving forward is your only real option, and you will be sucked into the black hole. 2. The photon sphere. This is where light orbits the black hole. Any light that enters this region will be captured and can't escape because of the black hole's gravitational force. 3. The singularity. This is where everything that enters the black hole is compressed down astronomically until it turns into a singularity. The singularity is a point in spacetime where the laws of physics, as we know them, break down, and we can't predict what happens next. The unpredictability of black holes. Now, what makes all of this even worse is the fact that each black hole you study will be completely different from the last. Sure, they tend to follow the same three-layer pattern, but the way they function could be vastly different. As it stands, if this were anything else, all we would need to do is bounce back on those telescopes and just review the basics in detail. But with black holes, you can't actually do that. Scientists can study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe into a black hole is impossible because anything that enters the event horizon is pulled straight into the singularity, where it is crushed into an infinitesimally small point. So, you can't exactly waste billions of dollars just to get a glimpse because, the second the probe gets close enough, it will be sucked into nothingness. Because of that obvious problem, scientists are left with no choice but to study these objects in a two-dimensional manner, even though they are three-dimensional singularities. To make matters even more challenging, there are also two major issues. 1. Each black hole is unique. 2. The laws of physics, as we know them, break down when we attempt to study the interior of black holes. The birth of a black hole. One of the most compelling theories about the formation of black holes is that they are made from collapsed stars. When a star exhausts its fuel, it can no longer support itself against gravity. If the star is massive enough, it undergoes a dramatic collapse, compressing all of its mass into an incredibly small space. This collapse leads to the formation of a singularity, a point of infinite density, surrounded by the event horizon, beyond which nothing can escape. This process is known as a supernova, a violent explosion that occurs when a massive star dies. While most of the star's outer layers are blown away in the explosion, the core collapses under its own gravity, creating a black hole. Interestingly, not all massive stars become black holes. Some turn into neutron stars, extremely dense remnants that are not quite as intense as black holes but still have incredibly strong gravitational fields. Whether a dying star becomes a neutron star or a black hole depends on its mass. If it is above a certain threshold, roughly 3 times the mass of the Sun, it will collapse into a black hole. Supermassive black holes, giants of the universe. While stellar mass black holes are formed from collapsing stars, there exists another category known as supermassive black holes. These cosmic giants, often found at the centers of galaxies, can be millions to billions of times more massive than the Sun. Scientists are still trying to determine how these supermassive black holes form. Some theories suggest they grow over time by consuming gas, dust, stars, and even merging with other black holes. Others propose they may have formed in the early universe from direct gravitational collapses of vast clouds of gas. One of the most well-known supermassive black holes is Sagittarius A*, located at the center of the Milky Way galaxy. It has a mass of about 4 million suns and plays a crucial role in the dynamics of our galaxy. Black holes and time dilation. One of the strangest effects of black holes, as predicted by Einstein's general relativity, is time dilation. Due to their immense gravitational pull, black holes can warp spacetime to an extreme degree. If an astronaut were to approach the event horizon of a black hole, an observer watching from a safe distance would see them slow down as they got closer. To the distant observer, it would appear as if the astronaut were frozen in time at the event horizon. However, from the astronaut's perspective, time would flow normally, until they inevitably crossed the point of no return. This phenomenon has been widely explored in science fiction, with movies like Interstellar accurately portraying the effects of gravitational time dilation near a black hole. Could black holes be gateways to other universes? Some scientists have speculated that black holes might not just be cosmic traps but could also serve as wormholes, tunnels connecting different parts of the universe or even parallel universes. This idea is purely theoretical and is based on solutions to Einstein's equations that allow for Einstein-Rosen bridges, commonly known as wormholes. However, there is no observational evidence to support this idea yet. If black holes do contain wormholes, the intense gravity and tidal forces inside would likely make them impossible for any object to traverse. The future of black hole research. Despite the many challenges in studying black holes, scientists continue to make remarkable discoveries. The Event Horizon Telescope, EHT, which captured the first ever image of a black hole in 2019, continues to provide valuable insights. Future missions and space telescopes may help us uncover even more about these mysterious cosmic objects. One of the most exciting possibilities is the discovery of primordial black holes, which are thought to have formed in the early universe. If they exist, they could provide critical clues about the nature of dark matter and the evolution of the cosmos. Conclusion. Black holes remain one of the most fascinating and enigmatic phenomena in the universe. From their mind-bending gravitational pull to their potential role in time travel and alternate realities, they continue to challenge our understanding of physics. While we may never be able to physically explore what lies beyond the event horizon, advancements in technology and theoretical physics will undoubtedly bring us closer to unraveling their mysteries. Until then, black holes will remain cosmic wonders, both terrifying and awe-inspiring. Produce enough energy to counteract the force of gravity that is constantly pulling inward, so the star begins to collapse on itself, contracting and becoming denser as it does. If the star is massive enough, this process can continue until it transforms into a singularity. To figure out the nature of black holes, NASA scientists turned their attention to the center of the universe, M87. Astronomers observed a really strong whirlpool of extremely hot hydrogen gas that was spinning at a stunning speed of 1.2 million miles per hour. The sheer force of the rotating gas disk should have caused it to fly apart in all directions, however, it didn't. Scientists found that there must be a massive mass gathered at the center of the galaxy to prevent this from happening. This enormous object weighed as much as 2 to 3 billion suns, and it must have been a black hole. But that doesn't seem to be the only theory about black holes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a rotating black hole. He showed that a rotating black hole wouldn't collapse into a point as previously thought but instead would form a ring of fire or a thin disk. The disk would rotate so rapidly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the ergosphere, and it's the region surrounding the black hole where the laws of physics start to break down. However, the most interesting feature of Kerr's model was that it predicted the presence of an Einstein-Rosen bridge, also known as a wormhole. This is a hypothetical passage through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, rather than being crushed to nothingness, they would be sucked down a passage through the ring of fire and shot out of a white hole into a parallel universe. To understand how this works, we need to look at the concept of space-time. In Einstein's theory, the reality we experience isn't made of separate elements but is interconnected, forming a four-dimensional fabric known as space-time. Objects with mass warp this fabric, creating a gravitational field that makes other objects move toward them. Now, imagine a piece of paper representing space-time. If you place 2 points on the paper and draw a line between them, this represents how objects travel through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole, a shortcut through space-time that connects two distant points instantly. Wormholes aren't just a science fiction concept. They are, in fact, a prediction of general relativity. Although no one has ever observed one directly, the reason is that wormholes are inherently unstable and would collapse quickly. However, the existence of an Einstein-Rosen bridge would mean that black holes are not just massive vacuum cleaners but could also be gateways to different regions of space-time. So, could we use a wormhole to travel through existence? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can travel through space-time. However, despite that, the theory of wormholes and black holes as pathways to different parts of the universe, or even to different times, has been a subject of interest and speculation among physicists for a long time. The possibility that there might be shortcuts through the fabric of space-time, allowing travel across vast distances or even into the past, could be revolutionary if we could achieve it. One of the most fascinating ideas in this field of study is the Kerr wormhole, named after the mathematician Roy Kerr, who first described Einstein's equations of gravity. This type of wormhole is essentially a hypothetical tunnel through space-time that could connect two distant points, like two different universes or even two different times within the same universe. The Kerr wormhole is ring-shaped, like the mirror in Alice in Wonderland, and could theoretically transport a traveler to another universe or some other time, where the laws of physics might be very different from the ones we're familiar with, but at the destination, that might just be normal. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, as we've mentioned before, it's also a topic of debate and discussion among physicists. Some have pointed out that wormholes, and especially black holes, might be unstable or difficult to cross due to the extreme radiation and subatomic forces surrounding their entrances. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity, not the quantum forces that govern radiation and subatomic particles. To understand the true nature of these phenomena, another theory is needed. one that can unite the laws of gravity with the quantum theory of radiation throughout the universe. This is known as a theory of everything, a single theory that can bring together both Einstein's theory of gravity and the quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for years. While there are many versions of what this could be, the one that has shown promise is superstring theory. Superstring theory combines gravity with the theory of radiation. The theory proposes that subatomic particles are actually tiny vibrating strings and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the intriguing things about superstring theory is that as the string travels through time, it warps the fabric of space around it, creating black holes, wormholes, and other extraordinary solutions to Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with quantum theory but also explains many of the mysterious phenomena we find in the universe. However, there's a catch. The extra dimensions of spacetime that superstring theory requires are so tiny that we can't even detect them directly. Although we can't directly detect these extra dimensions, some physicists believe they could hold the key to understanding the deepest mysteries of the universe. If superstring theory is correct, then our reality may be just one of many, with multiple dimensions beyond the 3 spatial and 1 temporal dimension that we experience daily. These extra dimensions might be curled up at incredibly small scales, so tiny that they remain hidden from our current experiments. One of the most exciting implications of this theory is the possibility that gravity itself could be leaking into these hidden dimensions. This could explain why gravity is so much weaker than the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force. While these forces operate at the atomic and subatomic levels with great strength, gravity appears disproportionately weak. If it is spreading across extra dimensions, this could provide new insights into why we experience it as such a feeble force. The future of wormholes and interstellar travel. If wormholes do exist, could we one day use them for space travel? Theoretically, yes. If a stable wormhole could be created and manipulated, it might allow for nearly instantaneous travel between distant parts of the universe. Instead of taking thousands or even millions of years to travel across galaxies, a wormhole could act as a cosmic shortcut, reducing the journey to mere moments. However, there are major challenges. For one, keeping a wormhole open would require an exotic form of matter with negative energy density, something that has yet to be discovered or created in significant amounts. While quantum mechanics suggests that negative energy might exist in tiny fluctuations within empty space, we have no practical way to harness or stabilize it on a large scale. Even if we could stabilize a wormhole, another problem arises: extreme tidal forces. As an object passes through a wormhole, the immense gravitational differences could stretch and distort it beyond recognition, a process known as spaghettification. Overcoming this would require a deeper understanding of quantum gravity, a field that remains largely unexplored. The search for experimental evidence. Despite the challenges, scientists are actively searching for signs of wormholes and other exotic spacetime structures. One approach involves studying the behavior of light and gravity near suspected black holes. If a black hole had a hidden wormhole entrance, it could create unusual gravitational lensing effects, bending light in unexpected ways. Another method involves searching for anomalies in high-energy cosmic rays. Some physicists speculate that if wormholes exist, they might occasionally allow particles to leak through from other regions of the universe, appearing as unexplained bursts of energy. The upcoming generation of space telescopes and gravitational wave detectors may provide new clues. Instruments like the Event Horizon Telescope, which captured the first image of a black hole, and the Laser Interferometer Space Antenna, LISA, designed to detect ripples in spacetime, could help confirm whether wormholes are real or remain purely theoretical. Could we one day travel through time? If wormholes exist, they don't just offer possibilities for space travel, they could also allow for time travel. Some solutions to Einstein's equations suggest that traveling through a wormhole could send an object into the past or future, depending on how the two ends of the wormhole move relative to each other. However, time travel raises paradoxes. One of the most famous is the grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, would you ever be born? Some physicists argue that the universe might prevent such contradictions through mechanisms like self-consistency, where events always unfold in a way that prevents paradoxes. Others propose that time travel could lead to branching timelines, where each trip to the past creates an alternate universe. While these ideas remain speculative, they push the boundaries of what we know about physics. Whether or not wormholes ever become a means of transportation, studying them brings us closer to answering some of the universe's deepest questions about space, time, and reality itself.